Solving a 3 by 3 system of linear equations. Consider the following system. Negative x plus 2x minus 3y plus z equals 4. Negative x plus 5y minus z is equal to negative 1. 5x minus 4y plus 2z equals 11. The first thing I'm going to do is actually label all these equations, or label all these rows by 1, 2, and 3. I am going to solve this using the style of elementary row operations, which will actually help you understand the tool of matrices later on. So I'm actually going to rewrite the system, or rewrite an equivalent system every time, using some operations that involve addition or switching of two rows, or multiplying one row and adding it to another row. The key now is to really keep things organized. The first thing I'm going to do is rather simple. I'm actually going to take equation 2 and multiply it by negative 1. So I'm going to keep equation 1, which is 2x minus 3y plus z is equal to 4. I am going to multiply by equation 2 by negative 1. That means I'm going to multiply both sides of equation 2 by negative 1. And we're going to store this as the new equation 2. And if I do that, I get x minus 5y plus z is equal to 1. I'm also going to keep my original equation 3. So equation 3 doesn't change either. It's simply going to be 5x minus 4y plus 2z is equal to 11. So as you're taking notes, make sure you understand how neat this is going to be. Everything's going to be very organized. It's not only going to be organized in rows, it's going to be organized in columns as well. Now I want this leading x right here, because it actually has a leading invisible 1. We would really like this in the first row. So now I'm going to switch equations 2 and 1, and we do have a mathematical symbol for that. We are simply going to write, take 1 and do a double-sided arrow and switch with equation 2. And now our new equation 1 has changed. It's going to be x minus 5y plus z is equal to 1. Our equation 2, our new equation 2 has changed as well. And our equation 3 has remained the same. 5x minus 4y plus 2z is equal to 11. Now that we have the leading 1 in the very first row, we are going to keep the first row. So I'm going to first take equation 1, take that same equation, and now we're going to use the addition method that involves equation 1 and 2, and the addition method that involves equation 1 and 3. So we're going to temporarily eliminate x. What does that mean? I'm going to take negative 2 times equation 1 and then add it to equation 2 and then store this in our new equation 2. If you do that, you get 0 times x, and we get 10y minus 3y, which is 7y. We also get negative 2z plus z, which is negative z. And we also get negative 2 add 4, which is positive 2. In a similar fashion, we're going to perform the addition method for equations 1 and 3. So we're going to do negative 5 times equation 1, add it to equation 3, store in this new equation 3. If we do this, we get 0 times x, and now we get 25y minus 4y. So that's 21y. We also get negative 5z added to 2z. So we get negative 3 times z. And then we also have negative 5 added to 11, which is 6. So at this point, what you want to realize is how organized things are. Look how organized things are. All the x's are in one column, all the y's are in a column, all the z's are in a column. Everything's labeled with 3 equations, 1, 2, and 3, 1, 2, and 3, 1, 2, and 3. So every time we rewrite the system, we tend to write all 3 equations. Now I'm going to look for patterns. There's a pattern with equations 2 and 3. It's hard not to notice it. I'm actually going to do something called, I'm going to do negative 3 times equation 2 and then add it to equation 3. First thing I'm going to do is keep the same equation 1, x minus 5y plus z is equal to 1. We're going to keep the same equation 2, 7y minus z is equal to 2. However, we are going to change the equation 3 by doing negative 3 times equation 2 from the previous equation 2 to previous equation 2. I'm actually doing this part right here. Negative 3 times equation 2 and then add it to equation 3. And then where are we going to store this? We're going to store this as the new equation 3. If you do that, you get 0 x's, and then you're going to add 0 y's. Yep, you get 0 y's. So the only thing left we have is positive 3z plus a negative 3z, so we get 0. We get a 0 over here is now equal to 0. Well, that's true no matter what. That's true. We already know that. So this is not any new information. This also tells you that the system is consistent. In other words, there will be solutions. And not only does this system consist of solutions, and the solutions are dependent. So this is a system that is consistent and dependent. The emphasis here is consistent and dependent. So we have a system that is consistent and dependent. Let's find that dependency relationship. It's not going to be too hard. What we want to do is realize that y depends on z. Z right now is our free variable. So we certainly could solve for y. So if you take our y, so take your equation 2 and solve for y. Y is now equal to z plus 2 divided by 7. There's your y. You could also write this as what? 1/7 z plus 2/7 if you want. You know, this looks like mz plus b. So this looks like a straight line in the yz plane. Let's look at x now. Well, we know y is dependent on z. Well, x is dependent on y and z. So can we find x? Let's find out. So I'm going to go back to equation 1. What we're doing right now is something called back substituting. I'm going to go back to equation 1 and solve for x. x is now equal to 5y minus a z plus a 1. But we know what y is. 5 times 1/7 z plus 2/7. Here's my y. We need to subtract a z, so 7/7 z. Might look a little confusing, but that says 7/7 z. I just subtracted a z, and then we're going to add 1. So how many z's do we have? We have negative 6/7 z and then plus 3/7 after finding common denominator. Oh, I take that back. We have 10/7 plus 7/7. 10/7 plus 7/7 is 17/7. Let's try that again. That should be 17/7. Alright. So really, all our solutions are going to be dependent on x. Let's write our set of solutions. We have our final set of solutions. It's going to be the set of ordered triples of the form negative 6/7 z plus 17/7, comma. Where's our y? Y is 1/7 z plus 2/7. And then what's our last representative? Our last representative is z, parentheses. Then we write this bar. This bar is read as such that z is a real number. So every ordered triple that satisfies the system of equations has to have these kind of relationships. Your x value is very, very specific, but you actually have to have this kind of pattern. Now your dependent variable could have easily been y. So you actually had two choices here. Notice for equation 2, you couldn't solve for z instead of y. And if you did that, you're going to get some different patterns here. You wouldn't have z anymore, you would have y. You wouldn't have y's here in every position. But in the end, it's going to represent the same ordered triples. There's actually an infinite number of solutions here. A good solution to probably look at is let z equal 7. If you let z equal 7, you're going to get an ordered triple that satisfies all three of these equations. If you let z equal 7, you'll get an x value, a y value, and a z value that will satisfy all three of those equations. What's another good z to pick on? I would pick z to be 0. If you pick z to be 0, you'll also get an ordered triple that satisfies all three of these equations. Now there are lots of choices for z. How many choices? Well, z is any real number. So if you really want to emphasize how strange this is, you want to let z to be any real number. So let me add the word any in here. Z is any real number. The key to solving these systems of equations is to be very, very neat. Notice if I had more space, my x's here would line up with the original x's. So notice the x column always is in the x column. The y column is always in the y column. The z column is always in the z column. And then the numbers over here are also in a column. We always write 3 equations in all these systems until you get to the end. Until the end, we get kind of sloppy. We go back substitution and then we actually find the ordered triple. But 1, 2, 3, 4 times I wrote the system with 3 rows or 3 equations. So keep that in mind. You're trying to write the system over and over again with new labels. And then eventually we back substitute and we get our ordered triple. Let's circle our final answer. The system consists of infinite number of solutions and the solutions are dependent. So this system is consistent and the solutions are dependent.